So we were doing part C of the first problem on the Calculus BC exam, the free response part. And so I'll reread it, because it says the region R, this is the region R, is the base of a solid. And I redrew the region R here, but with a little perspective, so we can hopefully visualize it in 3 dimensions. So it says for this solid, each cross-section perpendicular to the x-axis, right? There's 2 ways you could do a cross-section. You could cut this way, but that would be parallel to the x-axis. We wanted to cut perpendicular to the x-axis, or parallel to the y-axis, right? So if we cut it along a line like that, right? So they say each cross-section perpendicular to the x-axis is a square. So I drew a couple of squares here. That's one. So here, this would be the base, and since we know the cross-section is a square, the height has to be the same length as the base. Same thing here. So here, the height will be really high, because this is kind of maybe our maximum point in terms of the base width. And then it's still pretty wide there, and then it gets narrow again. So how do we figure out the volume of this solid, which is kind of hard to visualize, and it's in some ways easier to visualize than it is to draw. So you have to give me some credit. But anyway, what we do is we take the area of each of these squares, and I drew one of them here. You take the area of each of these squares, multiply them by a super small change in x, and that we know from everything we've learned in calculus, hopefully, that super small change in x, I'm trying to draw a little perspective, is dx. So if we multiply dx times the area of this square, that is the volume of this kind of part of the entire solid. And if we were to sum up all of these infinitely thin solids, we would get the volume for the whole thing. So how do we do that? Well, let's write our integral expression. So what is the area of each of these squares? Each of these cross sections. What is the area? Well, the base is going to be the difference between our 2 functions, right? This top function right here, that was sine of pi x. And this bottom function right here, that is y is equal to x to the third minus 4x. So the base of the functions, the base of this distance right here is going to be the difference between the top function and the bottom function. So each base is going to be sine of pi x minus this function. So it's minus x to the third plus 4x, right? Switch the signs. Minus x to the third plus 4x. So far, this might look pretty similar to part A. But what's the twist here? We want the area of each of these squares, not just this distance. So what's the area? It's going to be this distance squared. So we have to square this entire thing. So that's the area of each of these squares, and then we have to multiply them times a little bit of dx. And that gives us the volume for each of these, I guess, parts of the entire solid. And now what are our boundaries or integration? Well, it's the same thing as in part A. This is 0, this is 2, so the boundaries are pretty straightforward. So we essentially just have to evaluate this now. And just like in part B, I first tried to evaluate this analytically, and you end up getting a very, very, very hairy integral, which you can do analytically, but you have to know some power reduction formulas in trigonometry, you have to do some integration by parts, and it would probably use up all of the time on the AP exam. So since they said that a graphing calculator is required for some parts of the problem, I say, why not use our graphing calculator? Because the graphing calculator is very good at numerically evaluating definite integrals like this. So let's get out my TI-85 emulator again. Here we go. And I want you to see the keystrokes so that okay, so let me turn it on. Let me exit out of this. So we're going to use the calculus. We're going to use the calculus function here. So second calculus. And this function right here, this is definite integral. Very useful function to use. Press F5 to get our definite integral. And then we just type in the expression. So the expression, let me move it down a little bit. So it's open parentheses sine of, where's pi? Pi is, I haven't used one of these calculators in a long, long time. Oh, there it is. Second, pi x sine of pi x minus x to the third power plus 4x, all of that squared. And then this definite integral function, you have to tell it which is the independent variable, or kind of, where are we taking this, what variable are we integrating across, and that's the variable x. And then you just tell it the boundaries of integration, and we're done. So we're going to integrate from 0, from x is equal to 0, to x is equal to 2. And if I haven't made a mistake, I can hit enter and let the calculator do the rest of the work. And let's see what it ends up with. Notice, okay, and let's see. So that's the answer. That is the volume of this solid. It's 9.9783. So you could write that this is equal to 9.9783. And I'm pretty sure they want you to use the calculator, because frankly, computing the integral, that's kind of just, chug math, very mechanical math, although it's pretty sophisticated, but it would take you forever. But this is kind of, I think, what they wanted you to do. Set up the integral. Recognize that each of these squares, the area of each of these squares is just going to be this distance, the distance between the functions squared, and then you integrate that from 0 to 2. Let's see how much time I have left. I have a couple of minutes. So let's do part D. Image clear. Invert colors. Okay, part D. The region R models. Let me edit, paste. That's the actually. Oh, I didn't want to do that. Edit, undo, edit, repeat. Nope. Edit, undo, edit, paste. There you go. Okay, so I want to make this a little bit smaller. So what does part D say? The region R models the surface of a small pond. So that's the surface now. At all points R, at a distance x from the y-axis, the depth of the water is given by h of x is equal to 3 minus x. So essentially, it's 3 minus x is the depth, right? So at this point of this pond, the depth is just 3, right? 3 minus 0. And at this point, the depth is 3 minus 2, which is 1. So essentially, the pond is going to get shallower and shallower as we go further to the right. You could almost imagine it. Let me see if I can draw it again. So this is the sine function with some perspective. This is the polynomial function below it. This is, I should probably have drawn it. That's the x-axis. This is the y-axis. That's the y-axis. And so here, at the depth of the pond is given by the function, what did it say? H of x is equal to 3 minus x. So over here, the pond, the depth is 3. So if I were to draw, I'll do it in blue. So if I were to go straight down, the depth is, maybe it's 3. And then the pond essentially gets shallower and shallower as we go to the right. Right? So how do we figure out the volume of this? So over here, what is the depth of it? It's going to be 1, right? 3 minus 2. This is x is equal to 2. So here the depth is going to be 1. So if we take the cross section just along the x-axis, the depth is going to look something like this, but then this is the top of it. I know that's kind of hard to visualize. But anyway, how do we figure out what the volume of this lake is? And actually, I realize I'm pushing 9 minutes, so I will continue this in the next video. See you soon.